So this is the example where we have to calculate the change in speed. Okay. So change in speed from no load to full load. Right. Change in speed from no load to full load is given by is equals to, I will write it as no load speed is n naught minus n divided by n naught. Okay, n naught minus n divided by n naught into 100. But here we cannot calculate n naught and n because the data what we have is insufficient. Okay, if at least we would have the value of n naught, if we would know what is the motor speed at no load, we could have calculated n and actually we would have calculated the values. But here we don't have that sufficient data where we can calculate n naught and n. Okay, suppose if we had sufficient data, then we were supposed to calculate the speed values at both the conditions. Okay, so here I can write, we have the relation. Okay, we have the relation that EB naught by EB is equals to n naught by n. Okay, this ratio we have. Okay, or n naught by n is equals to EB naught by EB. Let us consider EB be the back EMF at full load. Okay, so EB naught is equals to, I can write V minus IA naught RA. I know what is no load current, okay, of the motor. So V minus, V is how much? We have 400 volts minus IA naught. IA naught we might have calculated. Here it is 3.18 amperes. IA naught into RA. RA is 0.6. Okay. No, my RA is, we'll consider 0.6 only. Equals to how much?
398.09.
398.09. Let us take 398 volts. Similarly, EB at full load is equals to V minus IRA, where IA is the full load armature current. So 400 minus IA is for, we have to consider it for motor, not for generator. Okay, so for motor IA is 51.18 into 0.6 is equals to, is 369.3 volts. So I can write it as now n naught by n is equals to 398 divided by 369.3. Or n naught is equals to This 398 divided by this value will be 1.077. 1.077 into n. Now substitute this value here. So change in speed is equals to 1.077 into, sorry, n into n minus n uh, divided by 1.077 into n equals to.
So
So
one
this,
point two.
so this value will be 7.2%. So the change in speed is 7.2%. Okay, so the change in speed from no load to full load is 7.2%. Now, if you consider the change in speed from no load to full load in case of induction motor, it will vary more than 20 to 30%. Therefore, this DC machine is known as the constant speed motor. That is the reason. Okay, so when you vary the speed from no load to full load, the motor speed will remain almost constant. Okay, you might observe this in the load test on DC motor, DC shunt motor. There you will observe the change in speed is very minimum. And when you conduct the experiment load test on three-phase and single-phase induction motor, you will understand the change in speed. Both motors are at 1500 rated RPM only. In our lab, single-phase induction motor, three-phase induction motor, DC motor, alternator, all rotating machines are at 1500 RPM rated speed. So when you vary the load from no load to full load, whatever the value we will observe, the change in the speed, change in the value of the speed, it is very much large in induction motors and very minimum in DC motors. Okay? Hence, DC machines are known as constant speed motors. Okay? We'll go to next example. Okay? A 220 volt DC shunt motor gives output of 18 kilowatts by taking input of, just a moment, I'm getting some call. Hello? Hello? ಯಾರು ಮೇಡಮ್? ಮೇಡಮ್ ಈಗಿಲ್ಲ, ಈಗ ನಾನು ಪುರ್ಸೊತ್ತಿಲ್ಲ, ನಾನು 6 ಗಂಟೆ ಮೇಲೆ ಮಾಡಿ, ನಾನು ಕ್ಲಾಸಲ್ಲಿ. By taking an input of 20.1 kilowatts. Okay. The field has 60 ohm resistance and armature 0.06 ohms. Find the efficiency and input power taken by motor when producing output of 8 kilowatts. And producing output of 8 kilowatts. So this is altogether a different type of example using Swinburne's test. Okay, so a lot of reverse calculations we should do in this example. So given V is 220, let me take this as P out 1 is equals to 18 kilowatt, because we don't know whether it is at full load or no load. So it is at full load or any other load condition. So at some load condition, it is giving the output of 18 kilowatts. By taking some input of P in 1, let me take it as P in 1 at 20.1 kilowatt. Okay, so the field has resistance RSH is equals to 60 ohms and RA, and this is hot resistance only, as 0.06 ohms. Okay, now I have to find out what is the efficiency to find input power 2 when output power 2 is 8 kilowatts. Let me take this as efficiency 1, first case efficiency, because I can calculate out, I know output, I know input, I can calculate efficiency. That we can do that. Okay, but we don't want that efficiency. I want efficiency at second load condition. Solution. No. When I know input and output, I can get the losses. Okay. Therefore, total losses WM1 is equals to, I will write it as P in 1 minus P out 1. Okay. P in 1 minus P out 1. So this I will write it as 20.1 K minus 18 K. So this will be equals to 3100 watts. Okay. Sorry, not 2100. Is it? It is 2100 watts. Now, these losses comprise of constant losses and variable losses. So, here, I know what is the input power. I know what is the input voltage. So very easily I can get what is the line current, IL1. I know what is the RA. Sorry, I know what is the RSH. So I can deduct, first you draw the DC motor. So input is 220 volts. So ISH, IA. This is I. Okay. So now I can write I1 is equals to P in 1 divided by V. First input divided by V. So first input is 20.1 K divided by 220 is equals to, so 91.36 amperes. So I1 is 91.36 amperes. Now ISH will remain same because voltage is same, resistance is same. So V by RSH, 220 divided by 60. 3.66 amps. Okay. Therefore, IA1, the first case armature current, is equals to I1 minus ISH. So 91.36 minus 3.66. So 87.7 amperes. Okay. So observe, I have the total losses known in the first case of load. I have armature current known in the first case of load. I have armature resistance known. If I deduct armature copper losses from the total losses in the first case, I will get constant losses. And constant losses we know will remain same irrespective of the load condition. Okay. So here we can do that. Okay. Therefore, constant losses WC is equals to, okay, WM1 minus I1 square RA. So I can calculate WC is equals to, so WM1 is 2100 minus I1 is 87.7 square into RA 0.06 is 461. So this equals to 2100 minus 461 equals to 1638.6 watts. So these are the constant losses. Okay. These are the constant losses. Okay. In second case, this is first case. You can write this as first case. Second case. In second case, what is that? P out 2 is equals to 8 kilowatts. Okay. Here, neither I know the line current nor I know the armature current. So getting copper losses in second case is not that straight away. Okay, it is not a straight way. Okay. So, but we can develop a expression where I can get IA. Because once I get IA, when I add those losses to the constant losses, I will get the total losses. Then when I add total losses to the output, I get PN. Once I get PN, I will get the efficiency. Okay, so that we have to do here. Okay. Let IA2 be the armature current. Okay. Here for my reference, I will redraw the circuit. Okay. Instead of changing slide every time. Now this is ISH, which is constant. This is I2, which is unknown. The input voltage is 220 volts. And this is armature current, which is IA2. Now what is IA2? Is equals to, I can write this as I2 minus ISH, that is I2 minus ISH value is how much? 3.66. Or I2 is equals to IA2 plus 3.66. Both are same. IA2 plus 3.66. Now, I know the output power. So input power P into is equals to, I can write this as P out 2 plus WM2. That is total motor losses. But here what is WM2? WM2 is equals to IA2 square RA plus constant loss, which I don't know, right? IA2 square RA I don't know. Therefore, I can't calculate what is um, WM2. Here, what is P into is V into I2, which is V is 220 into I2 is IA2 plus 3.66. Okay, and WM2 is equals to, I can write this as IA2 square, keeping IA2 as it is, into 0.06 plus constant losses 1638.6. Now substituting all these values in the P in 2. Okay, let me take this as equation 1. Substitute P in 2 and WM2 and P out 2, which is 8K in equation 1. Okay, so P into I will write this as 220 into IA2 plus 3.66 is equals to P out 2 is 8,000. Instead of K, I will write it as 8,000 because others are in other decimal numbers. Plus WM2, it is 0.06 IA2 square plus 1638.6. I will open the bracket here. So it is 220. We will get a quadratic equation in IA2. IA2 plus, yeah, 220 into 3.66 is 805.2 is equals to 8,000 plus 0.06 IA2 square plus 1638.6. So I can write an expression in IA2 square, that is 0.06 IA2 square minus 220 IA2, taking RHS to LHS to the other side, plus, so I have 8,000 plus 1638.6 minus 805.2. So it is 8833.4 is equals to 0. Now, upon solving this, what I get? IA is equals to, apply the formula, minus B plus or minus, okay, root B square minus 4AC divided by 2A. So minus B is minus of minus 220. So it will be 220 plus or minus root b square 220 square minus 4 AC minus 4 into 0.06 into 8833.4 divided by 2a divided by 2 into 0.06. So I will get two values of IA. This is IA2. So IA2 is equals to, you need not to do this, you can directly put in the calculator in equation calculations.
Sir, 40.6.
Two, both the values you can. One is IA2 is equals to
Sir,
One is
3626.06 and
30.6.
sir,
30,
40.6, sir.
40, 40,
Yes, sir. Another value is very big, sir.
40.6 amperes, and IA2 is equals to, let it be, you tell me,
3626.06,
amperes.
sir.
Let it. So which value you will choose?
40.6, sir.
Why not IA2? 3626.
It's
Because
very
the
big
value of
value.
armature current is so large that the motor become unstable. At 220 volts, you cannot get a value of current of 3000 amperes, 3500 amperes, right? So this value leads unstable operation. This value leads unstable operation. Okay, so therefore IA2 is equals to 40.6 amps. Now once I know constant loss, I know output, I know IA2, I can get the total losses. Okay. Therefore, armature copper loss IA2 square RA is equals to, so 40.6 square into 0.06.
$98.9.
It is 98.9. That's okay. So the total losses WM2 is equals to IA2 square RA plus WC is equals to 98.9 plus 1638.6. Yeah. So 1737.5. 5 watts. This is WM2. Okay. One case. So the total input of the motor, power input to motor P into is equals to P out 2 plus WM2. P out 2 plus WM2. This is one way. Second way, you know what is IA2, you know what is ISH. You can get the value of I2, multiply it with V. That is one more way. Let us check whether we will get the same in both the cases. So 8000 plus 1737.5. Okay. So it is 9737.5 watts, or P into is equals to V into I2. That is V into IA2 plus ISH. 220 into 98.9 plus 3.66. Do we get same or different?
Same.
There may be some difference in decimals, I think so.
9737.2.
22. I think I made some mistake here. 9737.2 you are getting.
Yes.
Okay, so
I'm
both are
getting different, sir.
one second, one second. I2.
So
One.
IA2 is 40.608.
Yeah. Sorry, I have made a mistake here. Even I was thinking the same. I was getting a different value. So sorry, 98.9 is copper loss. IA square RA. IA2 square RA. Yeah, 9737.2 watts. Okay, so both are same. Now efficiency. Therefore, efficiency 2 is equals to P of 2 by P into 100. So 8000 divided by 9737.5 or 2, anything you will take, because it won't make much difference. Is 82.16%. So any doubts in this?
No, sir.
Okay. So we'll move to another example. Last example on Swinburne's test. Then we'll move to next test. Okay. These are the different types of examples what you may get. There are no two types of examples except first and second of the same type. Okay. So why I'm taking all this is any type of example you may get in the question paper. Okay. One is solved example. I will solve it as it is because that is one important example. A 200 volt a 200 volt 1492 kilowatt, sorry, 14.92 kilowatt DC shunt motor DC shunt motor gave following Swinburne's test readings. Yeah, following Swinburne test readings. Running light, okay, and running light. I will write the values, okay. IA naught is equals to 6.5 amperes. Okay. Running light means no load. Okay, light load condition light running condition means no load condition. Okay, that is one more name for no load condition. Okay, ISH 2.2 amps. Okay. When armature locked, when armature locked, second. When armature locked, armature current is 70 amperes and uh, with 3 volts voltage between the brushes. 3 volts voltage between the brushes. Obtain the efficiency of motor at full load. Obtain the efficiency of motor at full load. Okay. So what do you mean by armature locked condition? This is a new terminology. So far we haven't seen that armature is locked in any case. We know that when we apply the supply, okay, when I give the armature voltage and the field voltage, motor starts running. Then how armature can be locked? Physically, I have to lock the armature so that it won't run. Then why should I do that? That kind of operation is known as blocked rotor operation. Okay, that is blocked rotor operation. We are blocking the rotor, and that is called short circuit test. Okay, that is called short circuit test. See, we have conducted open circuit and short circuit tests on transformers in the previous sem. What we did in open circuit test, we kept the secondary open. Okay, we kept the secondary open. There, the only voltage was available, current was not available. So V was rated, I was 0. In case of no load test, in case of short circuit test, we short circuited the secondary terminals of the transformer where the voltage was very, very minimum and current was very, very large. That is rated current we applied. Now, locked rotor operation is short circuit operation of the motor. It is valid for a very short amount of time, okay, on any motor. Short circuit operation or the blocked rotor operation, we will see even in induction motor. We have 2 experiments on that. We will be locking the rotor and we will be conducting 2 experiments. Okay, so before the start of the motor itself, I will make a mechanical arrangement so that when I give the supply, motor will not operate or the rotor will not rotate. So that is called blocked rotor operation. Once the motor starts running, blocking rotor is difficult. Okay, so blocked rotor operation has to be conducted before the start of the motor. Okay, so before the motor is started, we will be blocking the rotor. Okay, we will be blocking the rotor and we are not applying the rated voltage. You should observe here the voltage applied is only 3 volts, whereas the motor rating is 200 volts. If you apply full rated voltage under blocked rotor condition, then my winding will burn. The same thing what we observed in transformers. Okay, so the short circuit voltage applied was hardly 20 volts, where the rated input voltage was 230 volts. We did the same thing. So same concepts are conceptually all the tests are same. Only the way we conduct is different depending upon the machines. Okay. So understanding the open circuit test condition and short circuit test conditions is very, very important, especially in rotating machines as well as in static machines. Okay. Then why we need this? Observe, there is no RA given here. If RA would have given, then I did not need anything else to calculate the efficiency. The only thing missing is RA. Now observe, in the armature locked state, there is voltage applied, there is current given. Can I get RA? And this is hot resistance only because current carried by the armature is very large. So there is a heat temperature rise of the machine. So whatever the resistance we get RA is a hot resistance now. Okay, so this locked resistance I can calculate RA. Okay, so solution here note, you can say RA can be calculated from the data obtained with armature locked. Armature locked. So therefore, RA is equals to 3 divided by 70. It is 0.043. It is 0.42857. We will take 0.43. 0.043 ohms. Okay. Rest all things are same. Okay. You calculate. Take this as one. Okay. I know IA naught. I know ISH. Okay. The full load value you have to calculate, right? So the full load current is unknown. Again, we have to calculate IA in the form of previous case only. Okay. We will get a quadratic equation in terms of IA. There you have to find out IA. Okay, you just take it as homework and solve. Okay, rest all part is same as that of previous example. So only I wanted to tell this. Okay, so here I will stop. The session.